Thank you for joining the conversation today. My name is Revi Ofir. I'm a product manager for RISC-V processor IP at Synopsys. I'm joined by Carlos Basto, our architect and scientist for the RISC-V processor IP at Synopsys. Our team at Synopsys has been building processors for the last 25 years. A couple of years ago, we've moved that expertise into the RISC-V world and launched the RISC-V product portfolio that spans from embedded, low power through real-time and host application processors. Today, we'll be talking about a technology that we've implemented in our low-power embedded processors, and that will show some significant performance improvement. But it's really not only about the performance. What we wanted to actually try and do here is spark a conversation about how we can build more efficient implementations without having to rely on custom ISA extensions. So why is this important? Today's environment, we're seeing rapidly changing into intelligent systems across all types of segments, whether it's the consolidation of zonal controllers in automotive, robots becoming more human-like, or even wearable devices doing things that we couldn't imagine a few years ago. So 3 major trends that we're seeing in the market, and some of this has been discussed over the past day or two. The evolution of embedded design. While MCUs have always been really under pressure from cost, area, and power perspective, we're seeing a rise in heterogeneous compute requirements, whether it's control, DSP, and AI, all sensor fusion, pre- and post-processing. And many times, this has to happen on a single MCU or a single core. Edge AI growth. Edge AI is real. So take, for example, our fitness trackers today. They can monitor your steps. They can do your heart rate. But tomorrow, there'll already be personalized devices that are going to manage your gestures or make recommendations or even detect your stress levels. And so we're seeing more of this being built into edge devices. And of course, there's the RISC-V momentum itself. I know a lot of the conversations and the new things we're talking about are around HPC and data center. But one thing to remember is that microcontrollers were the first to adopt RISC-V. And they're actually leading in market penetration and in shipments today. And so while we see these rising compute and diverse workloads continue to happen, we still have this cost-constrained environment that we need to deal with. And so how do we actually meet that performance demand when every milliwatt, every square millimeter is important? So take you back to some university days. Pollack's rule says that the performance gain that you can get really only scales with the square root of a complexity. So take complexity as a measure of area, for example. So if we were to double the pipeline, for example, we would not get a double performance boost. We'd only get about 40% performance boost in reality. So the challenge is clear. Today's microcontroller options that we have in our toolbox, we could widen or deepen the pipeline. We could do multi-issue, multi-threading, multi-core. But really, those don't meet the stringent requirements that we see in today's embedded systems or embedded microcontrollers. To add to that, we would see significant power and area cost, as well as software effort involved. But what if we could break this paradigm? What if we could go linear and basically get a 1-for-1 complexity to performance boost? And that's what we want to show you today. And Carlos here is going to take us through to actually how we've been able to implement this in RISC-V.
All right, thanks, Revi. Can you guys hear me okay? All right, so my goal today is to convince you that we can indeed increase the performance density of these resource-constrained microcontrollers, delivering dual-issue class performance at very limited area increase. And in the end of the talk, we will have some data to quantify this claim. But before that, let's talk about instruction fusion. Very common technique, especially in RISC machines, that combines two instructions, decoding and executing them as a single internal operation. In this slide here, I'm differentiating between two types of instruction fusion. You can do fusion at the architecture level, at the ISA level. There are competing ISAs that are very famous or infamous for doing that. And in principle, one could go off and create ISA extensions to RISC-V to do exactly the same. The second type of fusion, microarchitecture fusion, you leave up to the hardware to detect these fusion sequences, and you do not need to add these ISA extensions. Our claim today in this talk is that the microarchitecture fusion is a much better framework for exploiting fusion in general, and therefore reducing the dynamic instruction count of these embedded microcontrollers. Just to give you an example, with microarchitecture fusion, you can fuse load and store instructions even if the addresses are non-contiguous in memory. Now, microarchitecture fusion does not reduce the static instruction count, so it doesn't get a plus in code density. But since it eliminates the need for ISA extensions, it's great for software compatibility because it allows a very simple implementation that may opt out of fusion altogether in higher performance implementations to execute on the exact same code base. So it's a great enabler for ecosystem development. Let's look into a few fusion sequences in RISC-V. Let's start with the simple sequence whereby you need to move an immediate value to memory. In RISC-V, this takes two instructions. You first have to put the immediate value into a register, and then you store this register into memory. If you look at this fuse sequence as a whole, it adheres to the RISC principle of two sources and one destination. So it's very easy to fuse. However, in the second example, you see here, this is the common, let's say, auto-increment load, right? You do a load, and you increment the load address by the load data size. In the combined sequence, we now have two destinations, one source but two destinations. And finally, the third example is a multiply accumulate. Over here, we have now three source operands and one destination. Note, these are just few examples. There are many other examples that falls into the second and third category, meaning that they need at least three source operands and two destination operands. So we may ask ourselves, well, if we want to add hardware to exploit this type of fusion, can we use those hardware even more efficiently to increase even more ILP? You see that the answer is yes, and in the next slides, we'll be explaining how would we do that. OK, what you need to do to enhance a canonical single-issue core with instruction fusion. The first step, you need to increase your fetch bandwidth. Most of these single-issue cores have a fetch bandwidth that is no greater than 4 bytes per cycle. So if you do not increase your fetch bandwidth, you'd be limited to fusing two instructions that are 16-bit compressed. And as a side note, if you are adding a RVV to this class of core to address edge AI type applications, for those of you familiar with RVV programming, if you want to eliminate the vset VLI from the instruction stream, since all the instructions in RVV are 32-bit, without additional fetch bandwidth, you will not be able to do that. Now, the second step, as we saw in the previous slide, you need to add more register file read ports. Here we are proposing, okay, we go from 2 to 3, and you add a second register file write port. And you augment the decoder such that it has the ability to decode fused instructions. Optionally, if you want to do load store fusion, you may want to multi-bank your memory system, your data closely coupled memory or data cache, to efficiently perform load pairs, store pairs type fusion. Okay, now what would it cost today, right? We are comparing now the cost of building a traditional dual issue versus the cost of building a core with our advanced instruction fusion approach. Our baseline is the canonical single-issue processor that has these characteristics: 2 register file read ports, 1 write port. The bypass network is the part of the core that connects the producers of results to the consumers of the results in the pipeline. And we are saying that this canonical single-issue core has a complexity C and has a number F of function units. How do we build a traditional dual issue in order core today? What we essentially duplicate, we add a second pipeline. And as a consequence, we double the number of register file read ports. We at least double the number of write ports. So we add more producers to this bypass network. And since we are doubling the number of consumers, the read ports are doubled, we see this quadratic increase in the complexity of the bypass network. And complexity here is a good proxy for area, a good proxy for power. And it's very common that in order dual issue cores, you duplicate some function units. ALU function unit is usually duplicated. With our approach, you don't need to duplicate the number of register file read ports. You only need to add another one, so you have a total of 3 read ports. And this is extremely, note that with these, you can not only address the fusion sequences that we identified earlier, but it opens up now the possibility of dual issuing instructions that together have no more than 3 source operands. And if you note that in RISC-V, a load instruction, for example, has a single source operand, which is the base address, we now can dual issue a load with any other instruction. We are adding a second register file write port. And because we are not adding any more producers to the bypass network, and we didn't duplicate the number of read ports, we avoid the quadratic complexity increase, and our increase in complexity of the bypass network is now linear. And in our approach, you don't need to duplicate function units. You can remain with the existing function units of your canonical single-issue core. All right, so let's see how would you build that, how you migrate to dual issue. First step, as alluded earlier, let's increase our fetch bandwidth, gives the ability to fuse these 2 instructions, even if they are not 16-bit compressed. We augment the decoder. We don't need to duplicate the decoder. It's a single decoder augmented with the ability to decode these fused instructions. And the back end of the core now is mostly agnostic to advanced fusion. Here in this example, I'm going to show 3 function units that exist in a canonical single issue: ALU, load store unit, and a multiplier. And we are not going to modify those function units. We're not going to add anything to them. We're just going to reuse what already exists. The gray boxes indicate latency, when these function units produce their results. All right, so let's look at some examples of what we can do, what this enables, right? What kind of dual issue we can accomplish. Suppose we have now a load and an add instruction that are independent, and together they have no more than 3 source operands, S1, S2, and S3. Now we can concurrently issue a load to the load store unit and an add to the ALU unit. Second example, store followed by a branch. Same story. Note here that the branch one of the operands is x0, which is always 0. So therefore, in total, this sequence here has 3 source operands, so fits into our requirements. So you resolve the branch in the ALU branch unit, and you issue the store to the load store unit. Finally, load and a multiply instruction. Again, together, only 3 source operands. You get the gist of it. The load is issued to the load store unit, and multiplier to the multiply function unit. All right, so what that all means in practice. We, as Revi mentioned earlier, we implemented that in our RMX class of cores, and we looked at what IPC improvements we see and what extra area we need to do that. The baseline is the, let's say, the single issue processor. So we observed only a 20% increase in standard cell. This was measured with physical synthesis. Note these are resource constrained cores, so 20% here in absolute terms is just, this just means there's a few tens of kilogates. This is very small. And we see a 25% in IPC as measured by CoreMark. So the CoreMark score of this class of cores is just shy of 6, which is very, very competitive in this space. And importantly, we achieve all of that without adding any ISA extension. So it's fully compatible with lower end implementations that do not have fusion at all. All right, I want to leave you guys with this slide here that essentially means implementation matters, right? Having open ISA, it's great enabler for ecosystem development, but it's really going to be through microarchitecture implementation in all these implicit resources depicted on this slide that we're going to tackle the stringent PPA requirements of these resource-constrained microcontrollers. With that, thank you very much. I think we have time for questions.
Great, thanks for the talk. This is Krista. So I just want to point out, I think what you're calling fusion, most people just call limited dual issue. There's no actual fusion going on. There's no data flow or control flow between those 2 instructions. It's limited dual issue, which, like say, MIPS R5K, Pentium 5, U plus V pipes. It's a standard pattern that we wouldn't normally call fusion. We just call limited dual issue. You're right to point out that full dual issue can be expensive, maybe not worthwhile, and some minimums. There's a good design point here. I just want to avoid people saying this is really fusion, and then saying, oh, RISC-V needs to do fusion. This is limited dual issue, which is a design point, like you said, is a good design point. But calling it fusion, I think, is a bit of a stretch.
But thanks for the observation, but we also do fusion as well, traditional fusion.
Just the examples you gave were limited
dual issue. The examples I gave was really for dual issue, but examples like decrement and branch not zero is a typical fusion example. We do that as well.
Yeah, I was looking forward to seeing those, that's why.
Okay, yeah. But thanks for the comment.
Did you have to do anything special for instruction triggers and data triggers?
That's a good point. So just like with with exceptions, whereby if you have exceptions on a fuse pair, you have to do something special so that you still maintain precise exception. And for data triggers, it's something similar. Yeah.
Thanks. I think we're out of time.
All right. Thank you very much.
Thank you.